All right, before we get started on the next lecture, we're going to recall a few things. Consider this example real quick. A bacteria reproduces once per hour. A sample starts with a single bacteria and grows from there. So we have this function b of t is equal to 2 to the t, right? So we have that our a value is 1, our b value is 2, and so our rate r is going to be b minus 1, which is 1, which is 100%. Okay. So b of t, that function describes how the population grows over time. So let's answer some of these questions. When will the population be 8, right? Well, it's pretty easy because if b of t is equal to 8, 2 raised to the 3, that equals 8. So t is equal to 3, right? When will the population be, say, 32? Well, that happens when t is equal to 5. That's kind of easy to see. Well, what happens when will the population be 20? Right? So let's see, 8 and 3, that's easy to see. 32 and 5, that's easy to see. Well, at 20, we're here on the graph. That is somewhere in between 4 and 5. Not actually sure what number it is, but it's somewhere in there. So if we look at some exponential equations, this is a very similar one. Instead of 2 to the x, 2 to the t, we have 3 to the x now. So also, I should say, with this example, we are leading up into what we're going to be doing in lecture 22 and how we're actually going to find the solution to this question about when the population will be 20. Not that one in particular, but the idea. So g of x is equal to 3 to the x. Does this equation, does the equation g of x equal 21 have a solution? Yes, somewhere it does. Does g of x have an inverse function? Yes, it does. It passes the horizontal line test. Right? And so we have g inverse of x, right? That function exists. So solving g of, well, that should be 21. Solving g of x is equal to 21 is the same thing as evaluating g inverse of 21. Okay? So what we're going to be doing is working with the inverses of exponentials, and they are logarithms, logarithmic functions. Now ignore this. That is old. Exam 2 is coming up. That is July 9th through the 10th. Okay. Okay. Lecture 22, logarithmic functions. So, the logarithmic function with base b is the inverse of the function b to the x. Okay, so we have some requirements. The same as the exponential function, actually. The b has to be greater than 0, and b cannot be 1. And we write it log base b of x. Okay, so another requirement, well, not really a requirement, but how we write things is y is equal to log base b of x if and only if b to the y is equal to x. Okay, so logarithms are just another way of talking about exponents. Okay, so when you talk about an exponent, you can be talking about a logarithm or vice versa kind of thing. Well, in this case, more logarithms are another way of talking about exponents. Anyway, let's look at some conversions. So let's go from logarithmic to, well, actually, no. Let's change into a logarithmic statement. So remember, y is equal to log base b of x. if and only if b to the y is equal to x. Okay, so let's look at this first example. 4 to the 3 is equal to 64. So you have log base something of something is equal to another thing, right? So we're going to fill in the blanks here. So log base b, so base 4 of 64 is equal to 3. Yeah. All right, let's go down to this one. Same deal. Log base, in this case, 9, because it's the base of our exponent. Log base b of 243 is going to be 2.5. Okay, we're sort of hopping back across the equal sign. So if we look at this one, 5 to the x is equal to 125. Well, we can rewrite this as log base 5 of 125. Jump back over, that's equal to x. Okay. K to the 4th equals 16. That's the same thing as saying log base k of 16 is equal to 4. Okay. So that's converting from exponential into logarithmic. What happens when we go the other way around? Well, convert to an exponential statement and then determine if it's true or false. I'm going to write this one more time. Y is equal to log base b of x equals b to the y, or sorry, if and only if, not equals, if and only if b to the y equals x, right? That's our conversion. So log base 7 of 49 is equal to 2. So that's 7 to the 2 is equal to 49. Well, that's reasonable. That checks out. 7 times 7 is 49. That's good. Let's look at this guy. Log base 4, so that's 4 to the negative 2 is equal to negative 16. Well, that's nonsense. This is 1 over 4 squared, and that definitely does not equal 16, or negative 16, either way. So this one does not work, or that's just not true. Let's move on to this one. Well, let's move that 3 over, right? Because it doesn't say anything for having a constant out in front of the log. So if we divide the 3 over, we get log base 2 of 1/8 is equal to negative 3. Okay. All right. So now this becomes 2 to the negative 3 is equal to 1/8. That checks out. That's good. Okay. 2 to the negative 3 is just the same thing as 1 over 2 to the 3, which is 1 over 8. Now this guy, log base 1/10, so 1/10 to the negative 5 equals 10,000. Well, that's not true, because this right here is 10 to the negative 1 to the negative 5, which is 10 to the 5, which is not 10,000. So that one is not true either. That one is false. All right. So there can be some problems when you go from logarithm into exponential, right? You'll notice we have some problems when we're trying to take the log of a negative number, log whatever base of a negative number, or having, well, we'll get into that later. So there just can be some problems. So you always want to check when you convert from an exponential statement to a logarithm statement, and vice versa, really vice versa. So let's do some evaluation. We'll get to the properties of logs in a short bit, and that will make why these conversions, why we have to check the conversions more clear. All right, so evaluate these. Log base 10 of 100 is equal to what? Well, if we put this into exponential form, we have 10 raised to the something equals 100. Well, that something is 2. You can't see it. I basically just filled in the box. So we're just going to say it here, and that's 2. Okay. Log base -3 of 81. So that means -3 to the something is equal to 81. This can't happen. It doesn't exist because -3 to any power will not give you positive 81, right? Because b value has to be bigger than 0. Okay, that was one of the requirements. Okay, actually, if I can fish that back out. Requirements are b has to be bigger than 0 and b cannot be 1. And this is our equivalence. Okay. Log base 1/2 of 8. Well, 1/2 raised to something is equal to 8. That something is going to be -3 because this is 2 to the -1 power. 2 to the -1, raise that to the -3, gets you 2 to the 3, which is just 8. Log base 19 of 19, that's just equal to 1. 19 to the something is equal to 19. That one's pretty straightforward. Log base 11 of 11 to the 9. Well, 11 to the something is equal to 11 to the 9. That has to be 9, right? Exponents have to match. Log base 2 of 0. Well, that means 2 to the something has to equal 0. That can't happen. So this does not exist. Log base 6 of 1. 6 to the something is equal to 1. Well, that can happen, and that would mean that that something has to be 0. Yeah, looks like I'm just filling in that box. It's 0. 6 to the 0 is equal to 1. Okay. Log base 5 of the square root of 5. So 5 to the something is equal to square root of 5. Rewrite this. This is the same thing as 5 to the 1/2. So this guy has to be 1/2. Okay. So now that we've gone through and just found out some things that don't work, some things give us positive numbers, some things give us negative numbers, right? Let's go for some properties of logarithms. So if we have log base b of x, here are some important properties to know. Log base b of 1 is 0. This is for any base b because b to the something is equal to 1. And that something will always be 0. Okay? Log base b of b, right? That's going to be 1 because b to something equals just b. That's 1, right? Doesn't look like it, but that's a 1 in the box. Anyway. Log base b of x is equal to x for any x, right? So you could have -1 in there. You could have 5 in there. You can have square root of 300 trillion, right? This works for any x. Another property that's important, if you have b raised to log base b of x, you get just x back for any x bigger than 0. This breaks when you have something less than 0. And we'll get into the reasons for that why in a minute also. So knowing these properties, let's take a look and evaluate some things. All right. Evaluate log base 3 of 3 to the 12. Well, it's the same situation as here. Log base b of b to the x is just x. So this guy is just 12. Okay. 5 raised to the log base 5 of 21. That's just 21. Well, 21 is bigger than 0, so it works out, and we can use our property. 4 raised to log base 6 of 36. Well, we can't use any property there, but log base 6 of 36, we know that to be 2. Because 6 raised to 2 equals 36. So this guy is 4 to the 2, which is 16. Okay, and then log base pi of pi to the e, that is just e. Our base is positive, use our property, everything works out. All right. Let's move on to solving some things. Well, let's look at this column first. Log base x of 1 over 64 is equal to -6. Well, put that into exponential form and we get x to the -6 is equal to 1 over 64. And so this is 1 over x to the 6 is equal to 1 over 64. So if we take the 6th root of 64, we get x is equal to 2 or -2, right? Yeah. But we can't have, so these are the possible solutions for x, but we cannot have -2 be a solution because x is the base of the log, so it has to be positive. So this is our only solution. Okay? Let's move on to the next one. Log base 3 of 2x plus 1 is equal to 4. So 3 to the 4th is equal to 2x plus 1. That is 81. 2x plus 1. 80 is equal to 2x. X is equal to 40. That one was pretty straightforward and easy. Nothing to double check, no solutions to be sure of. Okay, logs inside logs. Well, log base 2 of log base 3 of x plus 2 is equal to -2. Let's take care of the outer log first. So this becomes 2 to the -2. 2 to the -2 is equal to this inside bit, which is log base 3 of x plus 2. 2 to the -2, that's 1/4. All right, now let's change this into exponential form again. And so we have 3 to the 1/4 equals this inside bit. And then, well, there's not much you can do with that. So that's 3 is equal to, or x is equal to 3 to the 1/4 minus 2. Whatever that may be. Okay. So that's what happens when we solve some things. Now let's look at the graph of log base b of x when b is bigger than 1 and for when it is a fraction. Okay. So let's look at this one first. For b bigger than 1, we look like, well, actually, we don't look like this. This, if you'll remember, is the graph of an exponential function, b to the x, say. Y is equal to b to the x. Our logarithm function is going to look like that, roughly, right? It's the mirror image of our exponential because they're inverses of each other. So for a increasing exponential function, we get this as our logarithm function, log base b of x for b bigger than 0. Now for b less than 1 bigger than 0, I don't know if I said that right. B is bigger than 1 here, right? This one, when b is a fraction, the exponential function looks like this, right? It is decreasing. So our logarithm function is going to look something like, that, roughly. Again, it's the mirror image. If you reflect the black graph here over the y equals x line, you'll get something like this. It should be a little bit more curved this way, but it's a sketch. You get the idea. But anyway, that's what the graph of log base b of x looks like for b positive and bigger than 1, for b positive and b less than 1. Okay. So now let's go on to some properties of the graph of log base b of x. So the domain, range, x-intercepts, and other things. So this again is for when b is bigger than 1. Our domain, well, it goes from 0 to infinity, not including 0. Range, it goes everywhere, negative infinity to infinity. X-intercept, well, it does have one right there, and that happens at 1, 0. Why? Well, if you plug in 1 for x, well, doesn't matter your b value actually. Your y is going to be 0. Also, your x-intercept for exponential function was 0, 1. Right? So when they're inverses, you swap all the x's and y's. So let's look at this guy. This is for 0 less than b less than 1. Y-intercept, it doesn't have any. X-intercept, it does have one there. Asymptotes, it has a vertical asymptote at x equals 0. Increasing if b is greater than 1, and decreasing if 0 is less than b is less than 1. I should say x-intercept, y-intercept, asymptotes, all of these, all 5 of these work for this graph and that graph. Okay, both graphs. It is increasing, like in this case, if b is bigger than 1, and it is decreasing if b is bigger than 0 but less than 1. Okay, so let's go on to an example to really see what's going on here. All right, suppose we have a function f of x is equal to log base 2 of x plus 3. Okay, so log base 2 of x. If we just had this guy, we'd have a vertical asymptote. That's not a b. We'd have a vertical asymptote at x equals 0. But what we have is we have log of x plus 3. So the vertical asymptote is shifted 3 units to the left, right? So we have a vertical asymptote at negative 3. Negative 3. It also has a 0 at negative 2, right? You're trying to find out when log base of anything of 1 is equal to 0. So what makes this inside 1? 0. And also, so our b value is 2, so it's going to have this general overall shape-ish. When will this inside be 2? This inside will be 2 at negative 1, and so log base 2 of 2 is 1, so we also have another point here. So roughly, very roughly. Three, it'll look something like that, whatever. It's a sketch. That tail looks wonky. Never mind. I'm just going to leave it like that. That's my arrow and ignore all this nonsense. Okay. So there we have it. There is a sketch of f of x is equal to log base 2 of x plus 3. when trying to graph a logarithmic function, you need to find out where its vertical asymptote is, and then find out where its x-intercept is, and try and find another point to find out where that bend really happens. So there's that. Let's move on to some one-to-one properties of logs. So the function f of x is equal to log base a of x is 1-to-1, which means some things. If log of x, if log base a of x is equal to log base a of y, then x is equal to y. Right? If you have log base something, in this case a, if you have, yeah, it's self-explanatory. Never mind. Right. So let's use this to solve the following equations. We have log base 7 of x plus 8 equals log base 7 of 2x plus 12. Bases are the same, log base of something, log base of something. So we have x plus 8 is equal to 2x plus 12. Solve, and we get x is equal to -4. Okay, well, that was simple enough. Log base 5 of x is equal to log base 5 of x plus x minus 6. There should be parentheses here. So we would have x is equal to x squared minus 6. 0 is equal to x squared minus x minus 6. This factors into this guy. So x is equal to 3 or -2. We have a problem. We cannot have -2 as a solution because the domain of a logarithm function is strictly positive. So if we try and plug in -2 to check our solution, this goes bad. It's bad. So we can't do that. It breaks the domain rule. Okay. That's a very good property to use, very useful. So now let's move on to the natural log. We make this a little bit special because the number e is special. And so when it comes to exponential functions, we needed a bit more different notation. So we use ln of x to equal log base e of x, right? So it's the natural log instead of standard log. So all the same rules apply, right? Because natural log of e, right? This is log base e of e. That's just going to be 1. Natural log of e to the x, that's again putting it back into what we know and love. We already know this property, and that's just x. Right? Natural log of 1, again, same deal. Log base e of 1, that's equal to 0. E to the natural log of x, that's just equal to x, again, because natural log is just log base e, and it's a property that we already know. So we get this, right? Properties we already know that look just a little bit different because we use ln instead of log, but ln is a specific log, is log base e. So, all right. Now we have another one, the common log. The common log is base 10. So we use a decimal number system. So 10 is also another special number. We give a special logarithm function called the common log. So log of x is usually denotes log base 10 of x. So again, same deal here. Log base 10 of 10, that's going to be 1. Log of 10 to the 13, that's going to be 13. Log of that guy is -4. Yeah. And then this guy is 10 to the log 50, that's just going to be 50. Because remember, log is log base 10. And it goes back to these properties right here. Log base b of x, and in this case, it's log base 10. And the other one, it was log base e, and we just write it a little differently because we use them so commonly. But anyway, That's the common log. Natural log. We'll explore more logarithmic functions and things next time.